Put on your detective hat. We've got a mystery to solve. Find all pairs mn of positive integers satisfying the equation 2 to the n minus 1 times 2 to the n minus 2 times 2 to the n minus 4, etc., all the way down to 2 to the n minus 2 to the n minus 1 equals m factorial. Like any good problem, we'll start here with the smallest number we can use, n equals 1, and see if we can find a solution. On the left-hand side, we will only have one term in that product. So 2 to the first minus 1 equals m factorial. And since 1 factorial does in fact equal 1, we have found a solution to the equation. mn is equal to 1, 1. Next, what we will do is see if n equals 2 will provide a solution, and continue in this fashion until we start seeing that a solution might not be possible. If a solution is not possible after a certain n value, we have to prove that that's the case. So next, n equals 2. So in the left-hand side of this equation, we'll have two terms being multiplied together, 2 to the second power minus 1 and 2 to the second power minus 2. On the right-hand side, it equals m factorial. Going through the calculations here, we get 3 times 2 on the left-hand side, and 3 times 2 is equal to 6. So, since 3 factorial, which is 3 times 2 times 1, is the same as 3 times 2, we found a second solution to our equation. mn equals 3, 2 is a solution to our equation. With n equals 3, there will be 3 terms on the left-hand side, and we will do this continuously to find where we no longer get a solution. Okay, so let's check out n equals 3 to find out if that will in fact give us a solution. Numerical analysis of an equation is typically a good idea if you can, to get a feel for what the numbers are going to do as you continually plug in more integers. So for n equals 3, we have 2 to the third power minus 1 times 2 to the third power minus 2 times 2 to the third power minus 4 equals m factorial. With a little bit of calculation, the first two terms in this sequence of products of factors here will always be two numbers that are consecutive, so 7 times 6 here. But then the number that comes after that would be 4. Now, could we break up the composite parts of this into numbers so that it actually does equal a factorial? That's possible, but since we have a prime number 7 in this, it would have to be at least 7 factorial, which in this case, it is not. In fact, 7 times 6 times 4 is 168, and no factorial, no integer number factorial will equal 168. So we do not have a solution here for n equals 3. For n equals 4, I mean, it's possible that maybe just n equals 3 does not give us a solution, and we may be able to find a combination of factors that would give us a factorial. So for n is equal to 4, we have 2 to the 4th power minus 1, 2 to the 4th power minus 2, 2 to the 4th power minus 4, 2 to the 4th power minus 8, equal to m factorial. In this expansion, you'll always notice that the very last term, like here 2 to the 4th minus 8, will just always be 2 to the n minus 1 power, or in this case 2 to the 3rd power. Now again, we get 15 times 14, and then 12 times 8. And if we're able to maybe split up the composites of this number, we could maybe try to find if there is a factorial somewhere in there. But if you multiply these together, you get 20,160, which is not a factorial of any integer. So again, we have found an example of no solution. Now, if we begin to examine the different factorials in which these numbers live between, we would find that there starts to be a really big gap that starts to happen. So now we want to look at this in a more general sense. Let's look at the sequence of products on the left-hand side of our equation as a sequence Ln. Now we're going to observe that if we take this sequence Ln and write it out, we can factor out powers of 2 from every factor in there except for the first one, because the first factor there is odd. So, collecting all the powers of 2 from this product sequence, we get the powers of 2 to add to 1 plus 2 plus 3, all the way up to n minus 1. It's an arithmetic sequence, so we can use the formula for arithmetic sequences, and this would give us a power of n times n minus 1 all over 2. And the remaining part of that number would be an odd number. Now I'm going to introduce something you're probably not familiar with, and that's called the two-adic valuation of a number. In this case, take v sub 2 of x, and it's going to be basically asking you what is the largest exponent of 2 in the number x. We would call this the two-adic valuation of the number x. This is something that's very useful in number theory, especially with prime numbers, the p-adic valuation. So now the two-adic valuation of our sequence would be the largest power of 2 in our sequence, which is n minus 1 all over 2. So this is going to help us put some boundaries on the sequence that we're looking at. We know that our sequence is equal to m factorial. Now there's a formula that helps us evaluate what the two-adic valuation of m factorial is, and it's given by the formula that is an infinite sum of the floor function of the number m divided by 2 to the I power. The floor function is basically an integer value function that takes whatever m divided by that power of 2 is and gives you the smaller integer it's closest to. So the smaller end of the integers that it lives between. Now, this is going to be ultimately a sum of integers in this infinite series, and then eventually it'll turn to 0. The terms I'm talking about. So therefore, we could say that this sum has to be less than what the sum of the value of this would be if I drop the floor function. In other words, omit the floor function and just think of this as an infinite series. And looking at the infinite series without the floor function, it's an infinite geometric series, one that has a common ratio of 1/2 if I factor out m over 2. And therefore, I could write this infinite series using the geometric sum formula 1 over 1 minus r, or in this case 1 over 1 minus 1/2. And that gives the infinite series here to be m. So the p-adic valuation of m factorial must be less than the number m. Putting this together with the two-adic valuation we did on n minus 1 over 2, that is, the two-adic valuation on the sequence Ln, we can put those two things together to give us an inequality. And when you're dealing with number theory problems, especially ones that might or might not involve prime numbers, you definitely want to think about using inequalities to help you narrow down the possible values. So we know that the two-adic valuation of Ln is n minus 1 over 2. Again, that was the largest power of 2 that was in L sub n. And the definition of the definition of the p-adic valuation or the 2-adic valuation of m factorial was less than m. So putting those together, we get n times n minus 1 over 2 is less than m. Taking that inequality one step further by taking the factorial of both sides, we can then state that the n minus 1 times n over 2 factorial would be less than m factorial. All of this might not seem very motivated by any particular intuition. It's like, why are we writing all these down? But when you practice more and more problems like this, you begin to see some subtle procedures which will repeat themselves and are not so easily just abstracted and said, okay, follow step 1, 2, and 3. Now, we can make a couple of other arguments here, and we can reason this, and then this is one of the things that we would do with a number theory problem, is trying to put an inequality on something, is that you may not know where to start. So here we have a product of 2 raised to the nth power minus some number for each one of these terms. So if we didn't subtract the numbers from each of the factors in there, it would just be 2 to the n multiplied with itself n times. So that's obviously going to be larger than the 2 to the n's being with a number subtracted from them. So we can say that this inequality holds true, and on the right hand side it's 2 raised to the n squared power. So this sequence is less than 2 to the n squared power just by some simple reasoning, okay? Now we're going to make a claim about 2 to the n squared power. And we're going to claim that this is less than n times n minus 1 over 2 factorial for all n values greater than or equal to 6. The reason that we're going to make this claim is that it's going to lead to a contradiction. So the case of n equals 6 gives us 2 raised to the 6 squared power on the left, 6 times 5 over 2 factorial on the right, or 2 to the 36 power and 15 factorial. Now, it's easy to argue that this is true. 2 to the 36 power is approximately 6.87 times 10 to the 10th power. 15 factorial is approximately, let's see here, 1.31 times 10 to the 12th power. And that's less than 15 factorial. So we could make an argument here easily that this inequality holds true simply because of the 2 orders of magnitude difference that they have. So now for n greater than or equal to 7, we're going to use this inequality to strengthen our argument. So for n times n minus 1 over 2 factorial, we can imagine that this is equal to 15 factorial times 16 times 17 times 18, all the way up to n times n minus 1 over 2. So within 16, 17, 18, all the way to n minus 1 over 2, there are n minus 1 over 2 minus 15 terms in there. So we can compare that expression to 15 factorial times just 16 raised to that many number of terms. Now we have an inequality that tells us 15 factorial times 16 to that power is less than n times n minus 1 over 2 factorial. So if we were to multiply 2 to the 36th power times 16 raised to this power, we can state that that is less than 15 factorial times 16 raised to that power. And when we use a little bit of simplification to the laws of exponents on the left-hand side here, we can simplify the exponent and make an argument for the n squared. So take a look at this. If we clean up our exponents here on the left-hand side, we get 2n squared minus 2n minus 24. And that's less than or equal to n minus 1 over 2 factorial. But that has to be, that whole expression there must be greater than 2 to the n squared, because 2 to the n squared will always be less than 2 to the 2n squared plus or minus any other smaller terms. So here we can argue that 2 to the n squared is less than n times n minus 1 over 2 factorial. So now let's put it together. We started with the sequence ln is equal to m factorial. We were able to establish the inequality n minus 1 over 2 is less than m. And that allowed us to state that n minus 1 over 2 factorial is less than m factorial. So then we were able to state that ln, the sequence, is less than 2 to the n squared power. We were also able to argue that 2 to the n squared power is less than n times n minus 1 over 2 factorial, which is less than m factorial. However, m factorial is the sequence ln. So we get ln is less than 2 to the n squared, which is less than n times n minus 1 over 2 factorial, which is less than m factorial, which is equal to ln. In other words, ln is less than ln. A contradictory statement. This can never be true. Something can never be less than, strictly less than itself. So contradiction here tells us that there are no more solutions for n greater than or equal to 6. So therefore we've covered all the bases. Since m and n both have to be positive integers, we found the solution 1, 1, and the solution 3, 2. We checked for n equals 3, 4, 5, etc., and that didn't seem to work, and we proved that for any n greater than or equal to 6, that you cannot have any more solutions. So therefore, these are the only solutions that can exist. And therefore, we have completed this problem and the proof. If you want to become a good mathematician, a problem like these will really help you out. Hey, thanks for watching. I hope you enjoyed. Please hit that like, subscribe, and notification bell for more videos, and see you on the next one.